So I'm going to try and explain simplicity. So this is the third attempt at doing this in different conferences. This is not forwarding. Yes. Okay. So let's put some context on this. So it's in the context of Bitcoin script. So today Bitcoin has a smart contracting language, very simple language, which is a predicate that allows you to spend a Bitcoin. And simplicity is a alternative script which is more general. So it's more extensible and allows you to do more flexible things. It's, I was going to describe the properties. So it's lower level. So Bitcoin script is kind of large operations like is a digital signature valid and things like that, the most common operations. Simplicity is a very low level language, so it's actually lower than assembly language in the sense that it's talking about very low level objects like bits and bit strings and sets and mathematical operators and combinators. But it is designed to be formally verifiable. So because it has formal semantics, you can describe its behavior mathematically and mathematically reason about it using automated tools or semi-automated tools. And that's interesting because we want to get much higher assurance of what smart contracts are actually going to do, and not just in the cases that we can imagine and think about, but in all possible cases and make strong statements about that. So one thing is because it's very low level, there are many operations involved in doing even basic things. So even, let's say, adding two 8-bit numbers is a large number of simplicity operators. And so that can make the program a little large and the runtime a little slow. So for common macro-sized operations, like actually verifying a digital signature, doing a 32-bit addition, maybe big number libraries, so all of the common things that make up the implementation framework of a Bitcoin full node or Bitcoin wallet, there are a lot of library functions in there. And so what we can do with simplicity is to mathematically define them and then re-implement them in a native language like C and prove some things about them. So actually, another part here is the context. So simplicity started in 2012 at a concept stage. So some people may have heard about MAST, but simplicity is the actual rest of the picture that was in Russell's mind when he said the words MAST. And it's just a way to say that if you have a smart contract and it says that you can spend a coin in two different ways, like in the first way would be you would sign with a digital signature. In the second way might be a trustless escrow, so you go to an arbitrator and you do a multisig or something. Then you only really need to provide to the blockchain one of those branches because the other one doesn't really matter. You've got an OR branch, you can use whichever one is valid and prove that and not disclose the rest. So it's a general pattern for moving away from execution and moving more to proving the eligibility to spend a coin. So you don't need to reveal the whole program, you just need to persuade the full node and the interpreter that you have the authority to spend this coin. You're able to you prove that you would have been able to make the program execute and return true, you can spend the coin without having to see the whole program, without having to necessarily execute the whole program. So this is so I'm not necessarily expecting people to understand it, but I just want to show that it's low level and involves few operations and they're mathematical related operations. So it has a type system, so it's based on bit strings, but there's some mathematical concepts about types and you can compose things at a type level and build bigger types and bigger operators. So this is the full extent of its syntax. So it's a small mathematical language with 9 operators. So you can think about it more akin to like some basic math axioms, or in logical programming, let's say in a machine code, you've got ands and ors and nands and different operators, and you can build, in principle, anything out of that. So that's it. And then these are the semantics. So each of these operators has a meaning of what it's going to do, and you can describe what it's going to do mathematically. And it's necessary to be able to do that because you want to use a proof assistant to think about the overall behavior of a program built up using these mathematical operators. So now I'm going to give an example which is a very low-level thing. It's just adding 2 bits together, and it may have a carry if they're both 1. So it's written in words, which is just the different operators composed in a Lisp-like syntax, but there are different domain-specific languages that are equivalent, so don't worry too much about the actual syntax, but that's something you could type. And I wouldn't say it compiles because it's so low level that it's more like assembly. It's not doing anything clever to convert this text into this. Is a very mechanical and simple thing that's hard to make mistakes in. And what does that bit string mean? Well, it's the syntax tree for the program. So this is a syntax tree for the half adder. So it's using different operators and it's making different conditions and giving different outputs depending on that. And this is an 8-bit adder. So you can see that the program gets a bit bigger. It's not as big as you would think because it's able to reuse, not exactly functions, but it's able to refer in a DAG to the same subgraph of execution multiple times, so that the serialization, if the 8-bit adder needs to refer to a half adder, a dozen times, it can just do that, and there's only one half adder in there. And this gets a little hard to see, but this is the graph for SHA-256 implementation in Simplicity. And there's an enormous amount of reuse, so the actual execution size is incredibly small. So just to illustrate that fact, so that's the SHA-256 graph now, and there's no jetting of even basic things like 32-bit operations. This is all using basic type and logical constructs. And Russell O'Connor, who's the main designer and implementer of this system, he's been working on it on and off since 2012, most actively in the last couple of years when he's joined Blockstream. So he implemented in Simplicity everything he needed to verify an ECDSA signature. So SHA-256, ECDSA involves 32-bit adders building up to a big number library, building up to elliptic curve, and the serialization of the message, and the SHA-256 implementation, and the whole thing fits into 15 kilobytes of Simplicity binary, which can run reasonably quickly in its interpreter, and you can jet parts of it to speed it up. So what do you do with these binaries? Well, you run them with an interpreter, which is the Simplicity bit machine. So it's a kind of abstract virtual machine in a good way, where the abstract virtual machines invented by other projects like Ethereum are invented in a very bad way. So this abstract virtual machine has a formal definition. So you notice that the language is very low level and clearly defined. And so you can implement an interpreter for it. And actually what Russell did is to implement the interpreter in a language that can be translated into the same proof assistant language. And so he's able to make and has a formal proof that the Simplicity interpreter will correctly execute all possible Simplicity programs, which is a very strong claim that, for example, the Bitcoin interpreter cannot claim at all, as evidenced by the various bugs in opcodes that were disabled, in addition to which the Bitcoin's script system has a messy definition, so it's much harder to reason about it short of manually verifying things. So now the sort of mathematically defined interpreter execution environment is a little slow. So he also implemented a C version of the Simplicity interpreter. And then you have the question, well, is the C implementation correct? And is it the same as the Simplicity implementation? And there is a a subset of C called verifiable C, and a project by originally by some researchers at Princeton, which is an actively maintained project that helps you prove things about this simplified subset of C. And so we can prove that the simplicity interpreter written in C is equivalent to the simplicity interpreter. So that's ongoing work, but once that work is finished, and there's no kind of R&D barrier to doing that, it's just some kind of semi-automated systematic work to go through a very large DAG of what the interpreter does. Then you would have a mathematical proof that the C implementation is the same as the simplicity implementation, and the simplicity implementation of its interpreter always correctly executes all simplicity programs. So you can, from that, you get a kind of indirect proof that this interpreter is correct, and you can compile it. Because it's all mathematically defined, you can also reason about the programs you write in simplicity. So let's say you write a particular program to implement a call option, or to implement a vault, or something high assurance that mustn't go wrong. You can write mathematically constraints that you expect to be true, such as the only circumstance in which somebody could take the funds is if the option executes in their favor. Like if the price is higher than this threshold at this date, this should be the only circumstance that the funds should be released. And you can make a mathematical proof that that's the case. And you can prove lots of other things. So you can prove that any of the array bounds in the programming language will not overflow. So you don't need to do kind of runtime things, because you can prove up front that there are no circumstances where this program can misbehave by overflowing arrays. You can also prove things about its worst case runtime and its worst case memory usage, which is important for denial of service. So Bitcoin has a simpler model for managing and limiting execution cost from running out of control and becoming a denial of service issue, because all Bitcoin transactions are processed by all Bitcoin full nodes. And so you don't want somebody to create kind of DOS amplification with a sort of maliciously chosen script that consumes an enormous amount of memory, or is recursive, or doesn't terminate. So with simplicity, you can prove exactly the worst case runtime in memory. And you can even give other people the proof to verify. So what can you do with this? So if you think about this being integrated into Bitcoin, at the moment it's being integrated into a developer release of Elements. So you can, and that was done, released in August, a couple months ago. And if you think about, so it was designed in the Bitcoin context. So if you think about if this was available in Bitcoin, Elements is just an extended version of Bitcoin with some additional features. So if Bitcoin had simplicity today, and there are a number of things you could do directly in the simplicity programming language. So for example, what are current topics in Bitcoin? Schnorr signatures, Taproot. So if you had simplicity available today, you could implement Schnorr without needing a soft fork, because you could just directly implement it using the programming language. And as we've seen, even if you're going from the bit level, it's surprisingly compact. So if it's 15 kilobytes to go from just bits all the way up through a SHA-256 implementation, a big number library, elliptic curve library, if you have access to those libraries, so if you have a big number library, elliptic curve library, SHA-256 library as JETs, i.e. C implementations that you've proven correct and equivalent to simplicity implementations, then something like Schnorr would be incredibly compact, because it's just making a few calls and stitching things together in terms of serialization. So it would be perfectly practical to just run that, put that small program on each UTXO that wants to use it. But if you wanted to be more efficient, you could also convert the Schnorr small program into another JET. So you could formally verify a C implementation to be equivalent to it, and make a soft fork with a binary version of the same function. Now the interesting thing about that is unlike today, when you have a soft fork, if you don't upgrade your node, you are running at a reduced security level because you are not verifying some parts of it, of the script, right? So let's think about like, I don't know, CSV, or there are different opcodes that have been integrated over time, and generally speaking, to old nodes, they look like, well, I don't know what that is, so I'll just assume it's true. And so that's the kind of model of soft forks today. So if you don't upgrade, you are at slightly reduced security, and you're relying more on miners to, the majority of the hash rate to correctly honor those. But with simplicity, that's no longer the case, because if the upgrades are sent in special UTXOs, they can actually be fully understood by all the existing full nodes. They just get slower. So if you have a fast machine, or you don't need low latency processing of blocks, as long as it doesn't get too slow, you would not be forced to upgrade. So upgrades can be done more piecemeal and more permissionlessly. So you can think of simplicity as both a way to write more free-form scripts and as an extension mechanism for Bitcoin. So because of the relative compactness, you could even do more complicated things like well pairing, which is the construct used for ZK snarks indirectly. So different types of curves, basically, from the ground up using the big number library and so on. Now, those are kind of things that are heavy enough that you probably want to make a jet for them, but it just shows that you can pretty much build anything composable from these building blocks. And the other thing to say is that it's been integrated with full introspection capabilities. So today, a Bitcoin script, as well as having a number of opcodes, is intentionally limited for simplicity and predictability to not inspect the environment. So there is very limited statefulness. So the only state that's coming is not visible to the script. I mean, the script's environment is just to know the current block height and things like that. So with simplicity, you're able to introspect everything about the input transactions. And actually, you can also introspect the output transaction, which allows you to implement covenants, and so more interesting things. So some examples other than Schnorr and Taproot, another current topic is some SIG hash extensibility which is convenient for doing a more efficient variant of Lightning called L2. So that's being considered as a soft fork in Bitcoin, a separate soft fork to the Schnorr and Taproot soft fork. And with simplicity, you could just implement it, basically, because you have the ability to serialize what gets signed. You can choose exactly which parts of the transaction input or output to sign, and there wouldn't be a need to make a soft fork for it. You could do, so people have talked about a vault concept in Bitcoin. So it's, if you think about the management of coins, it focuses your mind about the security risks. So Bitcoin being immediately spendable presents security risks, as we've heard in some other presentations. So one way that banks have traditionally protected against that is to use a time-locked vault, so that the vault can only be opened with some notice, let's say. And with a vault in a Bitcoin context, you would be saying that there are some coins stored in a vault format, and if you need to spend them, you would first make an initial transaction that gets broadcast, and then, let's say, for a week after that, the transaction could be cancelled by other people and returns the money to the original coin holders. But if it's not cancelled, then after a week, the coin holder can spend it with some more accessible keys. If it gets cancelled, they have to go and get some cold keys and move forward from there. So it would help many kind of cold storage theft scenarios, because basically you can give cancellation rights to cancel a transaction to many third parties who can monitor the spend and attempt to contact you and ask if that's a legitimate spend. And if they can't contact you for a couple of days, they're going to cancel it. So it makes theft much harder to do. Of course, it has a trade-off, which is you can't You can't trade it immediately because you've got to wait until it's devaulted, so that's a trade-off. You could do something similar with hot and cold wallets. So a lot of exchanges, because of that fast spendability, they emulate vaults by putting a very small portion of the customer's Bitcoin they hold into a hot wallet and keeping the rest in a cold wallet. So with this kind of vault-like concept, you could make just basically a single wallet with a velocity limit and have the blockchain enforce that. So lots of things you can do with it, and prove the correctness, at least as compared to the constraints you want to articulate about how you expect it to behave, and get very strong assurances that that's the case. Another kind of example is that Liquid and some other systems have concepts of atomic trade, so either a cross-chain atomic swap or an in-chain atomic trade where the funds are, the buyer and the seller are trading directly but without having to trust the other party, so not cancel the transaction. In the Bitcoin script model, it's a little bit difficult to take a partial order. So if one person's selling one Bitcoin and the other person's trying to buy half a Bitcoin, you have a mismatch, and so it's hard to complete the trade. So with this kind of covenant concept, you can simply set it up so that you can take half of the transaction and the other half just is authorized to be moved forward without a signature. And so that would allow you to do partial limit orders. So we talk about what stage this is at. So it's been going on for a while. The original idea is actually quite old and related to MAST. We did a developer release in August, and Russell is busy working on JETs for all of the common library functions, so he hopes to release that later this year, which will make it more performant, basically, more dependable. The remaining work, it has the introspection features already. The remaining work is largely around more formal proofs for the equivalence of like the C implementation of the interpreter. There is a formal proof of the equivalence of the SHA-256 C implementation to be equivalent to the C implementation and the OpenSSL implementation. So they're just more formal proofs that can be built up around all of the components of it. And the other major thing that needs to be done is to figure out a good trade-off for the anti-denial of service aspects of it, so that it fits into the Bitcoin framework and can avoid overly long-running or overly high memory using scripts. So at least the ambition originally with this, bearing in mind that simplicity as a concept predates Blockstream by a couple of years. So the original ambition was to build a second-generation script system for Bitcoin by Russell O'Connor. And Russell O'Connor has been involved in Bitcoin since at least 2012, maybe 2011, and implemented a version of Bitcoin in Haskell, which is a more tightly defined language. And so it was just sort of reflections on the design of Bitcoin scripts and how he would ideally want to design a replacement script that is more flexible, but still provides high security assurances. So our idea is that, well, we will try it out in Elements and Liquid and deploy it in Liquid so that people can use it for liquid assets and sort of setting up more sophisticated trade assurance, like self-custody, trustless exchange mechanisms in Liquid, and prove out the technology so that if there's interest, eventually that might find its way back into Bitcoin. So basically, later this year, a second developer release of Simplicity for developers in Elements. Next year in Liquid, so that people can use it in Anger. And we'll see what happens after that. So, maybe in subsequent years, if this proves to be mature and interesting and popular, for that to eventually come into Bitcoin. I think personally that it has a lot of advantages. It makes, it's a soft fork that can subsume and avoid the need to do many other soft forks and avoid the kind of delays we see where Lightning, the initial version of Lightning was kind of waiting for CSV, and now L2 is waiting for SIG hash. So, there are other bottlenecks, like they have to implement L2, and they're still busy implementing Lightning, the current version of Lightning. So there are bottlenecks in all directions in terms of developer resources, but it at least provides a lot of flexibility so that if some other projects are interested to experiment with vaults or limit orders or something completely new and do it in a Bitcoin context. So while it's not, if this was available in Bitcoin, while it's not a sidechain, it allows you the kind of flexibility of what you might want to do in a sidechain, but to do it in Bitcoin directly. And because of the formal verification assurances, to do it without introducing inflation risk or other problems into Bitcoin itself. So there's a GitHub project, a Simplicity paper that's been out for a while now, and there are a number of videos online where Russell has presented about this at different stages of its evolution in the last year or so. So I'll stop there, and I realize it's a complicated topic, and that it depends on your background. If you're a programmer or not a programmer, if you're familiar with functional programming or not, or assembly language programming or not, provable security, proof assistance is a niche area even among programmers. So many programmers maybe wouldn't have tried a proof assistant. It's not a fully automated thing where you drop some code in and it says it's correct, but it helps you construct a proof. And once you have a proof, you can give it to other people who can verify it. So I guess I'll stop there and see if we have time for questions.
Check.
Hi, Adam. Thank you very much. At least for me, it was extremely clear. I have two questions. The first one, basically, Simplicity allows you to do zero-knowledge stuff like bulletproofs, correct? Is it correct?
Yeah, I mean, you could implement, there are two associations with bulletproofs at least. So one is that with access to JETs for big number library and elliptic curve operations, it would be pretty easy to directly implement bulletproofs as a Simplicity implemented extension without needing a soft fork, and maybe make C implementations, prove their equivalent, and soft fork those later. The second connection is going back to the sort of mathematical low-level nature of Simplicity, the base programming level. That is mechanically, it's simple enough and mathematical enough to be mechanically translatable into
FPGA?
Into basically like a mathematical constraint system. So if a bulletproof is proving in zero knowledge the execution and output of a circuit, and so you can translate the Simplicity low-level assembly language into a Boolean circuit and then make a bulletproof for it. So it would be interesting to be able to make bulletproofs for arbitrary Simplicity programs, basically. So that'd be another way to prove some things.
All right. So with this, actually what you have said on the sidechain panels, the idea of sidechains with a consensus verification system done in the Bitcoin itself with a zero-knowledge proofs, it can be done with a Simplicity, basically, isn't it?
I mean, it's pretty general, so you could do lots of things in it. It's still very Bitcoin focused, so it's not, it doesn't help you build up a database or rich statefulness and all this kind of stuff, because it's trying to retain the functional programming and controlled semantics. So yeah, I mean, you could implement a lot of different things that people have thought about as potential use cases, and you have some pretty good assurances of the behavior of the extensions because you have ability to mathematically reason about them.
And also it means that basically it will simplify implementation of like full Bitcoin node in a hardware like FPGA chips or something for Internet of Things. So basically what you said, it means that with the way Simplicity is designed, it's easy to implement Simplicity interpreter as FPGA's chip or something like that.
Yeah, I'm not sure. Maybe. I mean, you could accelerate it with custom hardware, I suppose, but you can also generally make it normally fast on general computers by making a C implementation of the same thing and then using the verifiable C project and put the output into a proof assistant and prove that the simplicity version is equal to the C version.
Yeah, I meant that maybe for Internet of Things, when you don't have a usual x85 or 86 or ARM processors and no C actually, but you still can have made things that will be able to verify at least simplicity scripts by themselves.
Yeah, maybe. It's not necessarily like super low level. Peter had a question.
All right, all the way in the back, Peter Todd hiding out. Nice hat.
I hear your brother liked it. Have you actually done any effort on, well, I guess I'd kind of call it UI UX testing, like actually run this by people other than very, 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 very smart people at Blockstream?
I mean, it's very far removed from the UI, I would say. It's
Well, remember, when I say UI, I mean like UI against programmers.
programmer UI, yeah. So I think there is quite a bit of work left to do in middle and higher levels. So if you think about this, it's kind of like programming in machine code or assembly, right? And there is a domain-specific language, which is still like a macro assembler, in fact. But there is probably a need for mid-level domain-specific languages that translate into it. But the risk there you introduce is the compilation and semantics of the mid-level language. You want that mid-level language, the domain-specific language, to still have formal semantics, for example. And formal semantics languages are unusual things to people. They're not used to programming in functional languages even, right? But I mean, the other way to look at it is that maybe this is more something that the equivalent, if you look at a sort of hierarchy of developers, and people use different levels of languages for different things, also productivity versus performance versus security assurance, that you've got like library writers who write assembly code, you've got maybe people that work at Intel and AMD who write some incredibly ugly code that microcodes assembly instructions. So maybe this is at the microcode level or something. And then you've got like library writers who write common objects that people will use. So I think you need sort of, maybe this is more useful for people who are doing the Schnorr extension, for example. They can do it using simplicity, and then the people who want to write programs can start using Schnorr more easily with a library interface.
I mean, as an example, like I've done very, very, very low-level hardware stuff, and when you look at, say, the design of Verilog or VHDL, there is a lot of thought put into trying to figure out how can we explain these concepts to people working on it. And when you read, for instance, the first page of the simplicity paper, right there you get a whole bunch of somewhat unpronounceable terms and mathematical notation. And I just think there needs to be some effort there. Maybe it doesn't have to be the core people doing it, but someone to say, what's the best way to explain this stuff and package it in a way that will get some adoption.
Right. Yeah. So this is my third attempt at explaining what it does. And so if Russell was up here talking about it, it would be worse because he would use more formal semantics, terminology, and acronyms that somebody who's a systems programmer in C may not recognize half the terms, right? So I think things are ultimately understandable, but they have to be explained in the terminology that bridges it to to what they already understand. So there are a number of novel things here, and people will have to get used to proof assistants, but they don't have an intuition about what a proof assistant does. So I think there's got to be more iterations of explaining what it does. Once the toolkit around it is easier to use, I think examples are a powerful way to get to understand things, because basically many programming tasks start by copying a program that you half understand, and then you modify it, and over time you become familiar with it and confident enough to write your own one of those things. They start by modifying an example, understanding how its proofs, following along with the example, like here's the program, here's what it does, and here's how its proof was constructed. Here's how you take the proof and give it to somebody else. Here's how they execute the proof verifier. So there's lots of things like that. Another kind of interesting thing you could do is to actually just, if you make an extension, rather than attaching it to every UTXO that spends it, you could maybe introduce a sort of a UTXO that contains it that's referable. So there are some details like that to work out as well. Another thing that's maybe interesting is one of the reasons that extension blocks are particularly dangerous is that they import non-determinism into Bitcoin. And if an extension block was itself implemented in Simplicity, and the only thing that the main blockchain or the miners had to do was to run the Simplicity interpreter, and the Simplicity interpreter is, prevents non-determinism, that would be a safer thing to do. So in a way of thinking, you could think about the Simplicity self-extensibility as allowing like little pockets of extension blocks arbitrarily inside. Another question?
I think we've run out of time for questions,
okay.
But it seems like a good time for my favorite quote from the movie Heist. I try to imagine what someone smarter than myself would do, and then I do that. So maybe that would help with Peter's question there. So thank you so much, Adam Back.